Hello, everyone. So this is the very first lecture of the topics in math modeling. So I call this lecture Zero, Modeling Change. So the goal of mathematical models, there are multiple goals to mathematical models, but mostly the goal is to study a particular real-world system or behavior of interest, right? Or you want, for example, you want to study the increasing or decreasing of certain populations, or you want to study the value of the real estate, something like that, right? When you study this particular real world system, you understand the behavior better, and that's probably going to help us doing some planning for the future. And doing that, we also reach some mathematical conclusions about the behavior and again predict the value of a variable at some times in the future. So for example, for the COVID-19 or any infectious disease, we build up a mathematical model. Later on, we're going to learn about something called the SIR models. That's the system of differential equations to help understand the breadth of the spread of the infectious disease. Right, you calculate the number, how many people are susceptible, which is the variable S, or how many people get infected, how many people recover from the disease, right? So the same model can be applied to various disease models like flu, dengue fever, or Ebola, or COVID-19, and many more infectious disease model. So though it's just some very small example of how you can use mathematics equations to model real world problem. But it's not always, it's never that simple, right? Because when you look at the world, it's a very complicated process, very complex process. We actually look at the real world data. And we don't just use, all of the information given to us from the world. You have to do some simplifications to come up with a mathematical model. So what you do is you simplify or do some simplifications to come up with some models, some reasonable model. And you use this model to analyze or do some analysis to come up with some mathematical conclusions. And with these mathematical conclusions, you can actually answer questions that you raise at the beginning of doing the model. Not only that, you can use these mathematical conclusions to interpret or predict or explain the future, right? So interpretations, and make some predictions and do some explanations about a certain behavior or a certain models, right? And after these predictions, you can go back and modify the real world data. Sorry, you can compare again with the real world data and see if that's matched with the real world data, or is there any modifications that we need to do. All right. So to construct a mathematical models, there's a few steps that you need to go through, but not always in that particular order. So the following step are just some basic steps that you need to keep in mind when you build a model. The first step, of course, is to identify the problem. Right, so you want to identify the problem that you want to work on. So what is the problem you would like to explore? Because typically, this is the very difficult step in a real life situation, because when you look at the physical phenomenon in reality, nobody hand you the model. You have to come up with the model, right? Usually you have to go through a large amount of data and identify a particular aspect of the situation study. And then you formulate the problem to allow for translations from the physical phenomenon to the verbal statement describe that problem into mathematical symbols. Okay. Now, after you identify the problem, you need to make some assumptions. Because the real world problem have so many variables and it's, again, a very complex system. So you need to make assumptions. You cannot hope to capture all the mathematical, all the factors influencing the problem. Right. You have to simplify by reducing the number of factors under considerations. Right. And to do that, you need to classify or identify and classify the variable you want to work with. So identify and classify the variables. So what I mean by that, so you need to ask the questions. What things influence the behavior of the problem identified in part one, right, in step one? And there's many variables. And if the variable that the model seeks to explain, well, we list that as dependent variables, and everything else you mentioned that, or you classify that as independent variable, right? So there's many variables and you classify them as dependent, independent, or neither. When you have neither, you can set them as constant or parameters that you can use some constant to replace that. And then again, you make assumptions by neglect some independent variables, right? Because the reason is that the effect of this variable may be very relatively small compared to other factors, right? So you can actually do that. And then the next step of making assumption is to determine interrelationship between the variables and submodels. Right, so for this step, you make some additional simplifications because sometimes, again, the system is very complex. You can break the model, the system down into submodels to make the study a lot easier. And we study one or more independent variables separately. And eventually, after all of the study, we can combine the submodels together. Right? And after this step of making assumptions, you can move on to solve for or interpret the model. And most of the time, the solutions that you look for is called the optimal solutions. You want to find the best solutions. Right, so optimal solutions. And so let me change this color to red. So just want to highlight the importance of the optimal solutions. All right, so you have seen this type of optimal solutions already in lower level math courses, right? So when you want to find the maximum value, the minimum value of some functions, those are the solution you obtain is called the optimal solutions. Okay. And now you solve, interpret the model. The next step is to verify the model, right? And you want to answer the following questions: that does the model address the problem that you raise in part one or in step one? Does it make common sense? and then test it with real world data. So for this step number 4 is usually in mathematics you have you dealing with some work example, and sometimes it doesn't make any sense at all. It's just some very complicated function that you want to find derivative, you want to find the integral of some very weird shape, or the area under the curve of some very weird curve. But in math modeling, you may want to come up with some model such that it makes common sense, it addresses the problem that you want to answer, and it fits or it matches with the real world data to a certain level, right? Because you cannot perfectly match all the real world data, you're just going to approximate the real world data. Okay. Now, after all of this, you can implement the model and then maintain the model if anything changes at all in the future. Right, so you implement the model. So the idea of this step 5 is that you explain your model in terms that the decision makers and user can understand if it is ever to be used in any situations or not. Because if you don't have a very common sense model, then nobody's going to use that. If your model is still very complicated that not many people understand that, then you cannot implement that. Implement model in the real world situations. Now, if you are able to implement the model, that means somebody use your model, then you need to maintain the model in the futures because, for example, if you build up the weather model, then the weather will change from years to years. So you may want to update the data so that it match with the latest data that you collect. So you need to maintain the model. Okay. And throughout this course, we're gonna build some model. Most of the time, we're gonna identify the problem, gonna make assumptions, we're gonna solve the model, and then we're gonna verify the model. Because it's still a very basic level of build up math modeling, so we're not going to care too much about implement this in the real world situations or maintain this in the real world situations. We just want to focus on can we identify the problem? Can we make assumptions to simplify the problem so that we can solve it and verify it with some real world data? Okay. So the art of mathematical modeling. Right? So the idea is that you always have to start with some simple model, right? Or you have to go through a process of model simplifications. That is, you need to restrict problem identifications. Right. So for example, I just want to go back to the infectious disease. So for flu seasons, there are so many factors that can cause a person to get sick. That you come in contact with some person, you get cold under the weather, something like that. So there are so many factors. So you need to restrict a certain problem and neglect some variables. Because you just cannot take all the variables into account at the same time. And then number 3, you combine effect of several variables, right? And then you can set some variables to constant. Right, so this is similar to step 2A. that we talked about earlier, that you classify the variable so that you have dependent variable, independent variables, or neither. Right, so it makes sense to have dependent, independent variables, and when you have neither, the neither variables can be set to constant so that you can just focus on dependent and independent variables in the model. Number 5 is to assume a simple relationship. Usually simple means linear relationship. And number 6 is to incorporate more assumptions later on. Right, so the more assumptions you have, the easier your model is going to be. Right? Now, because the end goal is to match your model with, or to test your model with real world data, right? So that now after simplifying the model, after you test the model against the real world data, you can refine the model or modify the model. The idea is to expand the problem. Right. So you make the problem or the model more complicated, and you can consider more variables or consider additional variables. And then consider each variable in details. Right, so at this step, for the simplifications process, you combine all the effect of several variables together. But in the model refinement, you just need to consider each variable in details, right? The more details you have, the more accurate your model is going to be. And then number 4, allow variations in the variables. Number 5 is to consider a non-linear relationship. Because the relationship between the variables in real world problems is going to be non-linear most of the time. It's very rarely that we have a linear relationship between the variables, right? But for the coursework, of course, we always want to start with some simple models such that we can use simple or linear relationship among the variables. And then to make the refinement for the model, you need to also reduce the number of assumptions that you're going to make for the models, right? And these two process go hand in hand, depends on the stage of your model building, right? Right. Some at the beginning, you want to simplify the model. After you test the model against the real world data, you want to update that or modify the model or refine the model. All right. So the next step is to study different models, right? So the first thing that we're going to study is called the modeling change, right? So what we see is that usually what we do, we look at the present value, you want to see the change, and all of this combined together to give you the information about the future value, right? So in other words, the future value is equal to the present value plus some changes. And this is what we're going to spend a lot of times on, that we want to model the change because we have the present value and you want to make the predictions for the future value, or you want to see the solution of the future value. What you need to do is to model the change, right? So often we wish to predict the future on the basis of what we know, right, in the present, and we add change that has been carefully observed. And so change can be also written as future value minus the present value. Right, so you can do this by collecting data over a period of time, plot those data, and then capture the trend of the change. Okay, and then you can go back and forth between these two equations to come up with the change, to come up with the future value. There are two models that we're going to look at, two basic models. The first one is the discrete time period. And we're going to use something called difference equations to model it. So difference equations. Right, so for different equations, we're going to use a lot, we're going to do a lot with sequences. And the second type of model that we're going to look at is the continuous change. And we're going to use something called differential equations. Okay, so that's the idea for this particular lecture. I just want to give you a very brief introductions to math modeling. There are certain processes that you need to go through, right? So you have the real world data, you make simplifications to come up with a simple model, right? And you use this model to analyze and then come up with mathematical conclusions or mathematical results. And you can integrate the results to make some explanation, to make predictions. And then again, you compare this predictions result with the real world data again, and then modify the model to make the model more accurate. And we're going to focus on two main models here. The first one is using difference equations. We're going to do with sequences, and it's going to happen or occur in discrete time periods. And later on in the course, we're going to work with differential equations. This is used to model continuous change. So that's it for me in this lecture. Please let me know if you have any questions. Thank you.